The final part of this lecture is going to be on velocity modulation. We've talked about how to modulate force. Now we're going to talk about how we modulate velocity, both in acute and a chronic fashion. Because remember, our goal is how do we produce power? The two parts that go into producing power is going to be force and velocity. Okay, so pay attention once again, just like we did with force, looking at the main ways acutely and the ways chronically, the major definitions, and then we'll wrap it up with a summary at the end. To begin with velocity modulation, the one thing to kind of remember or to understand about this is we can acutely modulate velocity, but a lot of it's going to come from chronic adaptations. There's some things we could do acutely, which we'll talk about, but really for a large part, it's going to be a chronic adaptation. So this is a velocity of movement is comprised of two components. We're looking at one, the rate the muscle shortens, and this is controlled by the cross-bridge cycling rate. That is, we've been talking about for the whole most of this unit, the rate of ADP release, and also the number of sarcomeres in series. Remember, the number of sarcomeres in series is going to be basically sarcomeres lined up in a row with one another. And then from there, the second part, how quickly repetitive movements are made. And this is controlled by one, muscle shortening rate, what we just talked about, and two, the muscle relaxation rate. So really what I'm doing with velocity is we're looking at repeated movements, repeated activity. Because as a muscle shortens, we want to see how fast, the muscle can shorten, but also then remember we talked about how a cross bridge actually works. I kind of did the motion with actin myosin with my arms, kind of like how they pulled one another, kind of like pulling a rope. So we're concerned with one, how fast it shortens, but how fast then the myosin could get set back up to go through it again. That's what we're looking at when we're talking about repeated activity or through the velocity of the movement. The shortening, but then how quickly you can get set back up to go through it again. Because as the muscle shortens, we just don't have just one myosin actin pulling one another. The myosin pulls an actin, basically goes from that 90 to 45 degrees, and then from there it gets reloaded back up and goes again. Reloaded back up, goes again. Okay, so that's what we're looking at with velocity. The biggest things here, like I've been talking about, ADP concentrations, and then the number of sarcomeres in series. One of the biggest things with looking at velocities, just said, is relaxation rate. What relaxation is looking at is not necessarily that the muscle's just resting and taking a break, but it's how quickly it's looking at muscle contraction. Relaxation is when it's getting set back up to go through another contraction again. That's what we refer to as relaxation. So with that, one of the ways we control relaxation rate, alter up the amount of SR calcium pumps that we have. Remember, the sarcoplasmic reticulum pumps the calcium out. Pumping calcium out is tied to relaxation rate. And so if you want to have a faster, just think about it like this. The faster a muscle could relax by getting calcium out, the faster the muscle can then go through another contraction. So this is really important for type 2 fibers, or fast twitch fibers. Because our fast twitch fibers, that's one of the characteristics of them. They have a complex SR development, which allows for, and they also have, remember this number right here, because we'll talk about this in pretty much every unit. But 3 times as much, or I should say type 2 fibers have three times as much calcium pumps as our type 1 fibers do. That's because they shorten 3 times as fast and they relax 3 times as fast. So calcium pumps are vitally important for the overall function of the muscle, especially when we're looking at velocity. Okay, so if you want to increase the amount of calcium pumps you have, do more anaerobic exercise. You want to decrease, do more aerobic exercise. That's why it's important, specificity of training. We'll talk about that in the last unit. You should do the type of training that's going to really impact what kind of competition or activity you're performing in. That's why if you have an anaerobic athlete, they should do very little aerobic exercise. Because the more aerobic exercise you do will then decrease the amount of calcium pumps you have, which in turn affect the muscle shortening rate. And actually the shortening and the overall velocity of the muscle, I should say. Because we're talking shortenings deal with ADP, relaxation deal with calcium. So I mixed up a little bit right there. But just know, if you're an anaerobic athlete, do as much anaerobic training as possible because that'll help maintain calcium pumps, which are vitally important for the overall functionality of type 2 fibers, which is the muscle fiber that's important more for power, strength activities. Just remember that number 3 times, because that's going to become important when we start talking through this chapter, but then metabolism and also cardiovascular as well. Next, so we talked about with phosphate concentrations. Well, we've already brought this up a little bit as well. ADP concentrations. Remember, more ADP in the cell floating around, less that could be kicked off the myosin as the muscle is shortening. So just remember, the cross-bridge cycling stops until the ADP is released. The higher the ADP concentration in the sarcoplasm, the less chance the ADP can be released. Hence, a high ADP concentration results in slow velocity. ADP concentration is controlled by the metabolic systems, which we'll get into in Unit 2. Okay, in a lot of ways, this is acute. This is also going to be kind of chronic as well. Because the more we train, the better shape we get in, the fitter we become, the more efficient all of our energy systems are working, the more it does help out with ADP and concentrations, phosphate, overall bioenergetics. That's a training adaptation. But also, this is an acute thing as well. If too much ADP is being built up, then that's going to affect the velocity. In a lot of ways, ADP is not going to affect, it's going to be more or less a problem from slowing down. Now, if you get rid of all the ADP, your velocity is not really going to speed up, because there's a certain speed at which velocity which they get shortened. We're dealing with, once the ADP builds up, it's going to start to slow down the velocity of a contraction. Just like with acute force modulation, the force velocity, same thing here with the opposite with velocity now. So it's just the opposite we're talking about, but still it's similar. That's the exact same. So it's the inverse relationship. If velocity is 0, force will be, if I should say if force is 100, velocity will be 0, and vice versa. The problem is, what happens if you have 100% force and 0 velocity? Then at that point you have 0 power, because anything times a 0 is a 0. Now with eccentric training though, you have a negative velocity. You're not going to have 0 power at that point. It's going to be really, really low just due to multiplying by negative. But with this, just know the goal is to match velocity and force to give the greatest amount of power output. Rate coding will also affect power. However, this is kind of more of an instantaneous one and done kind of deal. Thing is if you have a huge increase in rate coding, it will help out with velocity for that one time. Problem is, there's a good chance once that does happen, fatigue will take over and it will really impact overall power output from the muscle. It's kind of just enough to maybe, like I've used the example of saving some for later kind of deal. The saber-tooth tiger coming after you, kind of I said that earlier. Well, just think of it like this. Rate coding could be increased big time. Stimulation could increase big time for a muscle to increase the muscle shortening rate. But it might be just enough to get you out of the way of the tiger. For that one time the tiger leaps at you. It doesn't mean it's going to then help you out later on. So with this, Just know rate coding more or less. You're gonna modulate velocity other ways than so much doing through rate coding, unless it's kind of a survival, a needed thing that needs to happen. Getting now into the acute chronic modulations. So we talked about lattice spacing. Remember lattice spacing, looking at the distance between the myosin head and the actin? Well, if that space changes up, the distance changes from an optimal length, then it's going to negatively impact velocity. And usually it's not so much that they're going to get too long from one another, they're going to be short enough from one another, or doing it too close to one another. So you change lattice spacing, that's the distance between the thick and thin filaments, below optimum, and muscle shortening rate will decrease due to the physical constraints. Cramped quarters. Kind of an example I've used trying to run down the hallway that's only 4 foot tall as opposed to being a normal, 8 foot tall hallway. And so when you start to cramp up the quarters, well, one thing that is tied to that is hydration levels. Hydration has a major negative, or I should say dehydration has a major negative impact on a lot of things, but really on the velocity of a muscle contraction. We're not too sure exactly with muscle cramps what really causes. There's a lot of theories out there. I would say hydration is one that does play a part. Electrolyte imbalances also. When it says eat potassium, it'll help out. I think hydration is probably one of the biggest things. But we're not too sure on muscle cramps. But the point is, when we're talking about like those damages of the muscle like that, so hydration is one thing that will probably, to our knowledge, help out with maintain or not, helping out against muscle cramps. Hydration helps out with cell functioning. Hydration helps out with so many so many factors within the body that I would tell a lot of my students a lot of times, athletes should focus more sometimes on hydration, proper nutrition, and sleep than they need to on overall training. Okay, so just know, with muscle physiology, we'll talk about, some things, metabolism, when we get to that point. But within muscle physiology, talking just that, you want to maintain proper velocity, proper functioning of the muscle, getting away from cramps, and also the velocity, the shortening of the muscle. Make sure you drink enough water going into competition. You can also alter the number of sarcomeres in series. You can see right here is a good example of them. The top, there's only 2 in a row, as opposed to the bottom one, there's, 3, almost 4 in a row right there. I guess it's 4 right there. Okay, so one of the best ways you want to alter number of series, putting tension on the muscle. Tension is, well, it says later on, you can see in the slide right there, it's a stretch. But really, tension means just putting some kind of force in the muscle. That is either stretching the muscle, lifting the muscle, making the move, just having the muscle move around is basically putting tension onto it. That's how you could put more sarcomeres in series. And why that's important, as you can see, it says if one sarcomere shortens 5 millimeters per second, then 4 sarcomeres will shorten 20 millimeters a second. Because what happens is the whole entire muscle has to still shorten, no matter how many sarcomeres are in the fiber, in the row of the fiber itself. So the more you put in series means they're all going to shorten faster to get the same amount of shortening of the entire muscle that less in the series essentially would accomplish. Okay, so just know when you put more in series, that means then they're all going to shorten up faster because the muscle, let's just take the hamstrings for instance. The hamstrings attach up on the hip and then down below the knee. Okay, when that hamstring goes to shorten, that entire distance of the muscle has to shorten to accomplish the task of moving the hip and or the lower leg. Okay, so the entire muscle has to shorten to accomplish those movements. And so if you have more sarcomeres going from the hip down to across the knee in that series, they're all going to shorten faster than if you had less in that row right there. Okay, and so just know, more sarcomeres in series, means they're all going to shorten faster. It's going to increase the velocity of shortening. And that tension is accomplished via stretching, strength training, and overall just activity. It says a muscle placed on a chronic stretch will increase the number of sarcomeres in series. Muscle gets longer, the tendon gets shorter. A muscle that chronically has no tension placed on it will decrease the number of series, and the tendon gets longer. And the muscle gets shorter and the tendon gets longer. Okay, so if you want to get a faster muscle, do a lot more strength training, and that'll help out with the velocity. And the benefit, too, is if you put more sarcomeres in series, one is the velocity, but number two, more sarcomeres in series means overall more sarcomeres. More sarcomeres means more cross bridges, more force production. So putting muscles on a constant tension will increase force and velocity of a muscle, therefore increasing the power it can produce. That's why strength and conditioning is so important for athletes. Here's just showing you what just stretching alone, because the last slide says putting on a constant on a stretch of a muscle, and so they found it out via just having participants go through 10 weeks of training where all they did was just stretching. No resistance training, just stretching every day compared to a control group. And so even just stretching alone after 10 weeks, the stretching group was able to, well, one, have a greater sit and reach, so a greater range of motion. That should come to no surprise. But then look down, I'll come up to the next ones there. So you got 1 RM knee extension. Just by stretching alone, they got an increase in 18.2 kgs. That's a significant increase. You get greater endurance. But then also, because of the stronger muscle, there's where the 18.2 kilos on the 1 RM, they got a stronger muscle. We'll then look at standing along jump. The vertical jump, both of those are power movements. So that's telling us also, because the muscle got stronger, the muscle also got more powerful, partly because you got stronger and greater velocity. So more force and velocity was able to be accomplished in the muscles, therefore you got a more powerful muscle. You see 20-meter dash right there. The muscle got faster, they got faster with just stretching alone. Compared to the control group where we saw all the numbers got worse. So this is showing you just stretching alone minus resistance training has a huge beneficial impact has a major impact upon overall performance. The thing about stretching too is good is because of these numbers right here, take somebody who's elderly or someone who has some kind of disease where they can't fully go through muscle contractions for whatever reason. Stretching alone is good for those groups because they could help maintain the integrity of a muscle. Say stretching alone is beneficial for someone who, like my grandmother, who's 97 years old. Now, at this point, she is at a point where she is really, it's really difficult for her to get around. But, someone elderly like that, stretching is something that could help them out just to maintain just enough to get through some daily activities, just to, how like I said, maintain the integrity of the muscles. Lucky for her, she can still move around a little bit. But the older we get, it does get harder to do resistance training. So the stretching might be a great alternative to help those maintain muscle health as we age. Another thing you do is alter up the ATP release. That is, change up myosin type. Because what happens as you change the myosin type, then you're going to alter up the ATPase that's associated with that myosin. And so from that, then as you alter up the fiber type, you alter up the myosin or the ATPase, then it's going to alter up how fast you can release the ADP. You can see here the different myosin family and then the associated fiber type. So you see like type 1, slow oxidative, type 2A, fast oxidative glycolytic, 2X, fast glycolytic, that's human, type 2B, non-human. Some old papers you'll see human studies, sometimes they'll say 2B, but now we know that 2B is in animals, 2X is in humans. But nonetheless, having fiber type switching, you'll start to alter up that. But remember, whatever protein's associated, the enzymes there's always an enzyme associated with that protein. So you alter up the myosin, alter up then the ATPase. Therefore, you alter up then the ADP release. Here's the velocity differences between myosin types. So this is one of those older papers right here looking at with 2B in there. But just know, for the sake of this, just know, type 2 fibers shorten, have about 3 times the velocity of type 1. And I say about because if you look, 2A has a shortening of 2.5 seconds compared to 3.5 of 2B. So you just round it up, or you do the average, you get 3. Okay, so type 2 fibers have 3 times the velocity of type 1 fibers. Just remember that number 3 because we'll talk about that here coming up. If you do want to change myosin types, going from 2X to 2A to type 1, one of the things you can do is increase the amount of continuous activity. That is, the more activity will be slower the myosin will become. Increase the amount of activity means do more work in terms of exercise. Okay, when we exercise, we sometimes think that it's all based, we exercising for X amount of time. Like, oh, I went to the gym for an hour today and lifted for an hour. No, you were in the gym maybe for an hour, but you only lifted for maybe 10 minutes because you do, 10 exercises, 8 reps, 3 sets of 8. We'll say that. Well, it only takes you, 10, 15 seconds to do one set, and then take a little breather, do another set, breather, so forth and so forth. Okay, so you're not really doing 60 minutes of continuous work. If I went out for a run for 60 minutes, then yeah, that is 60 minutes of continuous work. Okay, so if you want to change, do more work in your activities. If you want to become more type 1, I should say, have a greater amount of volume of work within your exercise. That'll help change from type 2A or 2X to 2A to 1. You also deplete the muscle cell of creatine. By doing more activity, more work, you will deplete the muscle of creatine. Creatine is the main energy source or the substrate for one of our power energy systems. So if there's no substrate available for an energy system to use, then you're going to switch to other energy systems then. Okay, so get rid of the creatine, you'll become more type 1. Now, the opposite, you want to become more glycolytic, more power, so more 2A, 2B. One you could do is inactivity. It says usually applies only to those which are slow due to chronic activity. So things like spaceflight, nerve damage, muscle damage. Doesn't take a whole lot metabolically to keep type 2 fibers going. So therefore, if you want to become more type 2, become a couch potato. Lay around, do nothing. Now, a lot of negative benefits will come from that, or negative outcomes will come from that benefits, but that's what you can do. Since all of us in our field are not couch potatoes, we're all exercise enthusiasts. You want to become more type 2 fibers, perform short bursts of fast, high-power movements. That is resistance training, sprints, high-intensity interval training, things of that nature. You also take hormones. So you can take thyroid, adrenaline, or adrenaline-mimicking drugs, steroids, clenbuterol, ephedrine, cocaine. Those things will all switch fiber types as well. But for us, we're going to do it number 2. The main way you're going to switch, become more type 2, is just doing more anaerobic activities. High intensity, low numbers, but high intensity with high bursts of movements, resistance training, things like that. Okay, so why have different myosin types? It says we have the right myosin for the right job. That's why. Okay, so I know I talk about us having 3 fiber types, but in all actuality, it's not a perfect set of 3. It's not like we just like a stair step type notion of 3 fiber types. Yes, we have the three distinct ones, but there's a huge gray area in between all of them. And we have this continuum of these fiber types because it allows us to perform such a wide array of movements. We have such, like it says right here, great versatility as humans. We could do a lot of movements fast. First we could do a lot of movements, and we do a lot of those movements either fast or slow or in between. So we have the right myosin for the right job. But now, if you want to break it down and look at, all right, since we do have this wide array of myosin types, we have this great versatility. We do need to kind of look at it, separate out a little bit though. Okay, if I want to do power movements, then the fast myosins will be better for power movements than the slow myosins. If I want to do more endurance activities, then slow myosins will be more beneficial than fast myosins. So like I said, we have these right myosins for the job to get the job done efficiently. But if we're looking at just power right here, fast myosins are always going to be better for power movements, strength movements. But let's look at power right now. And so to break it down, know that the force of one cross bridge is equal, force of one fast cross bridge is equal to the force of one slow cross bridge. And that's true. Okay, I know I said that fast myosins produce way more force than slow myosins. That's true too. Let me explain. If you're looking at the force production between just one cross bridge, just one myosin and one actin interaction, the force between fast and slow cross bridges are the exact same. The force is the exact same between the two. Now, when you're talking about overall fast muscles, they're larger than slow muscles. So therefore, that's why there's more force coming out of fast twitch fibers than slow twitches, because despite being 1-for-1 in force production, due to the simple fact that fast myosins are larger, or we have more of them, and by nature of being type 2 fibers, that's why they produce more force overall. Okay? But now moving on, because we're talking about power. Remember, power, force multiplied by velocity. So we've established that one fast cross bridge is equal to the force of one slow cross bridge. I've already brought this up. Note number 3 says the velocity of one fast cross bridge is 3 times the velocity of one slow cross bridge. So the power of one fast cross bridge is 3 times the power of one slow cross bridge, or 3 times the power for the same amount of mass. That's the key word, looking at the same amount of mass. The difference becomes slow twitch fibers always have greater mass, so therefore overall more force and more power output. It says even if you triple slow cross bridge numbers, fast myosins still give more power. And the reason being, it says at any speed of muscle contraction, fast sarcomeres will have more attached cross bridges. Fast can just grab quickly, the sliding acting a lot faster than slow twitch, than the slow myosins. And you see the graph on the left is the force velocity, and then the one on the right is the power curve right there. It says optimum power from fast cross bridge occurs at 40% max force output. Optimum power for slow cross bridge occurs at 20% of max force output. And that's what the power curves are showing right there. So fast myosins, they have their optimum power when almost half of all their cross bridges are attached. And it's just by nature fast, that's what makes them, once again, another part why they're called fast myosins, because they have the ability to make attachments at a faster speed than the slow myosins can. And we see the power curve, the optimum power output is done when there's about 40% cross bridge attachment for our fast myosins. Slow cross bridge is only about 20%. So a lot of times you'll see a lot of strength and conditioning books, workouts talk about doing activities at 30% of strength, 30%. Well, usually they get that by just averaging 40 and 20%. That's where you see the 30 if you ever see that come about. That's why a lot of times, you might be doing some plyometric training with a little bit of weight, but not a whole lot. just trying to get a little bit more explosive coming out of there. Well, that's what they're trying to hit at right here. Okay, so just keep this in mind. Fast cross bridges can make attachments at those faster rates compared to the slow myosins. So once again, don't need to worry about all the math on here. This is just kind of highlight the point right here. It says assume that the force output of a single cross bridge is 1. Therefore, the force of 100 cross bridges equals 100. Assume the velocity of a slow cross bridge is 1. Assume the velocity of a fast cross bridge is 3. Therefore, max slow power is 100 times 1, so 100. Max fast power, 100 times 3, 300. In theory, tripling the slow cross bridge, hence force would be 300, and thus max power would be 300 times 1 equals 300. However, if 100% of cross bridges are attached, velocity is 0, therefore power is 0. Maximal power of the slow occurs when 20% of cross bridges are attached. We just heard that. And max power of the fast myosins occurs when 40% of cross bridges are attached. Hence, max functional power of 100 fast cross bridges would be 100 times 3, because that's 100 cross bridges, 100 force, multiplied by 3, because that's the velocity, so 3 times as fast, multiplied by 0.4. That's the optimal power range. So you do that, you get 120. Do the math for slow myosins, so 100 multiplied by 1, the velocity, multiplied by 0.2, so 20%, and you get 20. So if you were to then triple it, let's say 300 slow myosins, if you were to do the math, so 300 multiplied by 1 by 0.2, you get 60. So you're still nowhere near where fast myosins power output would be. Thus, to get the same power output as 100 fast cross bridges, one would have to increase slow cross bridges 6-fold to get the same amount. So what this is saying, and like I said, don't worry, it's all about the math. Just don't really need to know is the 40%, 20%, 3 times this velocity. What this is saying is that fast myosins give you a greater power output at the same given amount of mass as a slow myosin. And to get the same amount of power output, you'd have to increase slow myosins to an unphysiological level pretty much to get the same amount. So in terms of power sports, power activities, your fast myosins are more, I'll use the word, efficient for that type of sport, for that type of activity. I know I've brought up the word efficient before, but I'm being specific here. Fast myosins are way more efficient at power output or for power activities than slow myosins. Okay? And so when you're talking about endurance, we'll see there in a sec, endurance type activities, slow myosins are more efficient because, well, when you're dealing with endurance, endurance activities tend to have a low force output, or isometric activities. They don't require a lot to keep going. Okay, so in terms of this, you almost could say that slow myosins are more efficient for endurance type activities, but one's not more efficient than the other. Now, I do have the word economical here because you could use the argument that slow myosins are more economical. Point being, it says that low force, slow cross bridges are more economical because they use less ATP over the unit of time. Remember, we said there's 4 places where ATP is used: sodium potassium pump of the nerve, the muscle, calcium pump, and the ATP or the cross bridge cycle itself. It says all cross bridges use 1 ATP per cross bridge cycle. ATP used per unit of time equals the number of cross bridge cycles during that time period. So it says during every single slow cross bridge cycle, the fast cross bridge completes 3 cycles. Remember, 3 times as fast. Thus, for any time period, slow myosins make 1/3 the number of cross bridge cycles. Thus, use 1/3 the ATP that fast myosins use. So you could use the word economical. I could make the argument there. You make an argument they are more economical than fast myosins because they use less ATP, but not more efficient. Okay, you don't want to go into a power activity with a lot of fast myosins. They're not going to be suited. with a lot of slow myosins because they're not going to be suited for power activities. Flip-flop of that, you don't want to go into endurance type activities with a lot of myosins. They're going to burn up way too much ATP throughout, so they're not going to be efficient for that movement, for the activity. But slow myosins, I will say, are more economical because they use less ATP, but not more efficient. Depends on what you're doing. We have the right myosin for the right job. And so to wrap it up, which is more efficient, fast or slow? This is a word I like to use a lot. Depends. Okay, that's one of the best scientific terms you could ever learn. It depends, especially in kinesiology and exercise physiology. It all depends on what's going on. Okay, I use that word as a joke, but it's also true. It gets you to start thinking deeper and deeper and deeper. Okay, so which one's more efficient? Well, for high power activities, fast are more efficient. For low power, long duration, slow are more efficient. But they're not more efficient than one another. They're suited for that activity. To conclude with velocity, just remember, when we're looking at velocity, we're looking at really two parts. One, shortening rate, and also two, relaxation rate. We want to see how fast the muscle is shortening, but then also how fast relaxation, that repetitive movement aspect. Okay, and so when we're looking at shortening, that is getting ADP being released. And then when we look at relaxation, calcium pump, calcium uptake back in the SR is going to be a major important part of that. Okay, so with velocity, we're looking kind of as a two-part of this. One, how fast it can shorten, but then two, how fast it gets set back up to go through it all again. Okay, and just remember the few ways we can change things up acutely. One would be, altering calcium pumps. Another one could be ADP concentrations. But then a lot of your velocity modulations are going to be chronic, putting more sarcomers in series. That's done majorly via putting tension on the muscle, strength training, stretching, so forth. And just remember then too, we're looking at fast versus slow twitch myosins. Fast twitch myosins shorten 3 times as fast as slow twitch. So therefore, because if you look at the force comparisons, one cross bridge to one cross bridge, force is the same, but due to fast myosins having 3 times the rate of shortening versus slow myosins, therefore they're going to have 3 times the amount of power given the same amount of mass as slow myosins. But the thing about fast myosins, fast twitch muscles, is they're generally larger than slow twitch. So therefore, because of that, you're getting a significantly greater, more stronger muscle, more forceful muscle, and a more powerful muscle, I should say. That's just due to fast myosins having a faster velocity, but then a greater mass overall compared to slow myosins. That's why they're more beneficial, more efficient, I could say, for power type activities. Contrary to that, your slow myosins are going to be more beneficial, more efficient during endurance activities because they use only a third of ATP than fast myosins do because they shorten 3 times slower than fast myosins. Remember, every cross-bridge interaction, every cross-bridge cycle, I should say, 1 ATP is being used. So because of that, slow myosins, because they shorten 3 times slower than fast myosins, they're using a third of the ATP that fast myosins are. So they could be more economical, you could say, as well, but not more efficient. They're more efficient for endurance activities, just like fast myosins are more efficient for power activities. Okay, but one's not more efficient than the other. We have the right myosin, and like I said, I used the stair-stepper analogy, is that when you're looking at the myosins, it's not a perfect little, stair-stepper type of, hierarchy of muscle fibers. Okay, we have the 3 distinct ones, yes, but within that, we have a huge gray area in between all of them. We have a big old continuum of muscle fiber type. And that allows us then to have such a great versatility within our system to be able to perform a lot of different movements. Along with that as well, we're able to perform all those movements at different speeds, fast, slow, in between. That's what makes humans so, versatile compared to other animals. It's just due to the ability of just how we're able to perform all these movements is because we have the right myosin for the right job. We just have this very complex system that just has this big, like I said, continuum, allows for the smooth movements, the smooth articulations, allows to perform the activities the way we are able to as humans. So just keep that in mind when you're learning this and studying this, kind of keep just this within that framework right there.